continue. Okay, so just a short announcement. I'm guessing that this time does not work for a lot of you. So I'll send out a survey today. If you are watching the video, please go and check your Canvas and respond to that survey by the end of Friday, and we can update the timings. Okay, so let's start. I will copy down the question, and as usual, I'll just discuss the overview of how it should be approached, but I won't do any algebra. Okay. So here's problem one, which says that this is an elevator for a business jet aircraft shown in figure one. So you have quite some details in figure one. You don't need to be overwhelmed by that. You'll reference that as required. So first, let's look at the question. Estimate the elevator control power, knowing that some parameters are given. So we don't need to worry. We don't need to like read all of the math at once. Just look at the targets that it's elevator control power that we are looking for. And if the airplane has the following characteristics and XCG is given, then we need to estimate the most forward CG. So there are two targets that we want to reach in this question. One of them is elevator control power and one of them is most forward CG. And it's written in the figure that the numbers in parentheses are in feet while the ones outside parentheses are in meters. So be cautious about that. Like we won't be deducting any serious amount of like score for that, probably nothing. But yeah, it's like in the exam, you'll face a deduction. So let's work backwards. What is elevator control power? If you recall from the class, elevator control power is defined to be the coefficient of moment to the pitch, like the contribution of the elevator trim tab to the coefficient of moment, which is Cm delta E. Times like the coefficient part, not the constant part. So there is no constant part. We only contribute the contribution as Cm delta E times delta E because the constant part is coming from the tail itself. So note that elevator control power is given by tail efficiency times horizontal volume tail ratio times CL alpha tail times tau E. So everything is very similar to the tail except we have an additional efficiency parameter which depends upon the area of the tab to area of the tail. Okay. So there is enough amount of data to help you calculate. I can be like the assurance that I can give you is that this can be calculated with the amount with the data that's provided to you. This can be calculated with the data that's provided to you. Be cautious that if you go and look at the data here, then this is small CL alpha t. So and remember that this is capital CL alpha t. So this is the 2D one and that is the 3D one. So you need to convert back from 2D to 3D before you attempt the question. Don't make that mistake. And this will probably show up in your midterm as well. So be cautious of that. This is like one of the most common places, like one of the most common points where a lot of you make mistakes is that C smaller alpha t is for 3D lift coefficient and oh sorry, my bad. C 2D lift coefficient and C capital alpha t is for 3D lift coefficient. So we do have horizontal volume tail ratio, we do have lift tail ratio. I've told you that if you can't find efficiency of the tail to be explicitly given, you can assume any number between 0.9 to 1, but to make my and graders life easier, just assume 1. We are going to evaluate, like we are just going to, it helps us like to keep the numbers in the same range. Finally, you need tau E. Now, if you recall, then you need to go and find out this graph for tau E. Tau E will never be provided, and this is like S tab versus S tail, the ratio for that. So obviously, to get here, we need to travel on the x-axis. And for that, we need to find out two things, S tab and S tail. So I think that's a doable job. Is that is that one of the places that you face problems, Jesus?
No.
Okay. So moving forward, once let's say you have found S tab and S tail, then you go ahead and drop a perpendicular, get the function point, and roughly estimate tau e. So you'll most probably land up in a similar range to the exact answer. So just don't fear that there is an exact answer or something. Approximation works here. We are going to look at the steps. So write your homework neatly. I'll also put out a notice for that. Okay, great. So I think once that is done, we have all the terms that you need to estimate the elevator control power. So that part of the question is done. The next question says if the airplane has the following characteristics where the CG location is provided, Cm naught is provided, Cm alpha is provided, C cap L alpha is provided. Estimate the most forward CG location if alpha max is going to be 15 degrees and delta max is going to be plus minus 25 degrees. So first of all, remember, just to clarify, I think this has been discussed in your class very clearly that when do you apply maximum deflection? Has it been discussed in class?
Yeah, yesterday.
Definitely. So you know that maximum deflection is applied at takeoff. And whether that has to be positive or negative, think about these questions. These are the questions that you need to think while solving and not making mistakes. Like when is maximum deflection going to happen? When is maximum angle of attack going to happen? Why are they both required at the same time? And why is the most forward CG location so crucial in that phase? That is the takeoff, basically the run from the runway and the takeoff part. So it's already given that so since you already have CM alpha and CL alpha, you can recall that you can find out the neutral point using CM alpha and CL alpha. I'm not going to exactly give you the formula, but you should remember all of these things. It's there in the note sheet that you can relate the static margin. So if you have the values to calculate static margin, if you have CG, then you can get the neutral point. And once you have the neutral point, then what you're going to do basically is going to write down the entire moment coefficient equation and basically yeah, and basically you would say that I don't want any pitching moment at maximum deflections. It should still be stable. And then based on the most forward location, and then you'll assume that in this configuration, my CG is in the most forward location. And I would obviously want my CM alpha to still be like negative. My static margin should still be negative, right? So what is the maximum limit I can breach so that it doesn't go zero? That's the question. Anything that I did not cover or that I should take up in more depth? Let me just have a look at the questions. When drawing the planform area of wings, do we project the wing shape onto the fuselage? I get that. Um, these are some general questions which we'll take up at the end actually. Okay, so the next question. So the next question says, the PA-32 Cherokee 6 airplane is equipped with a rectangular wing and an all-moving horizontal tail, no elevator. So something that's going to be tricky here from the get-go is that there is no elevator, okay? And it's an all-moving horizontal tail. So exactly, it's like the entire tail is an elevator. It's not like there is no elevator. It has the following characteristics, the span of the wing, the surface area of the planform area of the wing, the span of the tail, the planform area of the tail, the incidence angle of the wing, the CG location, and the location of the aerodynamic center of the tail from the CG is provided. The airplane weighs so much so forth, cruises at some speed, cruises at some height with speed so. You may assume that CMSE of the wing is negative 0.09 and alpha naught, zero angle of attack, zero lift. So just to guys, let you know, guys, that probably this could be one point of confusion for all of you. So when it says alpha naught lift wing, this means like angle of attack at which lift is zero on the wing. So if you place the wing at a negative angle of attack, then you're going to get zero lift at negative 4 degrees. What does this mean? This means that 0 is equals to CL naught for the wing plus CL alpha for the wing times alpha naught lift for the wing. And this is provided to you. So basically it's saying that you can get a ratio between CL alpha wing and CL naught wing by writing it down this way. Negative CL naught wing by CL alpha wing is equals to alpha naught LW. This is this is something which might be difficult for the first time for you to approach or understand. I hope that's clear now. So we have been given some information. If it's too overwhelming, I suggest that this is also one of the practices. I suggest that just go ahead and make two columns that this is the wing column, this is the tail column, and this information is provided about the wing, this information is provided about the tail. You could also take it up a notch. You could call this, you could make another table like B, S, I, so on and so forth for different parameters such as wingspan, platform area, incidence angle, so on and so forth. And then you can fill up this table to make sure, okay, I don't have these values, I only have these values. Now, what is the question actually asking? Determine the required tail incidence angle to trim the airplane at cruise. Okay. Estimate the most forward CG location if ITail max is going to be plus minus 25 degrees and alpha max is going to be 15 degrees. So at trim, first of all, let's see the required tail incidence angle to trim the airplane at cruise. So first of all, you need to find out um, what is missing here. The entire CL is missing here, like the lift coefficient at that configuration is not given to you, right? But we can actually find that. How can we find that? So it's simple. It's very simple. First of all, the first sub step is understanding what is trim. Trim is lift equals weight. From here, you will get CL at trim, which is the total lift coefficient of the aircraft at trim. Total lift coefficient means contributions coming from the tail, wing, like whatever approximation we apply. I'm not going to be very explicit, but be cautious. So this is the first step you have taken, that okay. And the second step is we know that CM trim is going to be 0. That's the definition of trim. That weight is balanced by lift and our aircraft does not rotate or move along. So these two pieces of information should easily allow you to solve for the angle of attack that's required for trim as well as the incidence angle of the tail that's required for trim. And to do that, you would need these terms. You would need like CL naught, CL alpha, CM naught, and CM alpha, which are very easily derivable from the geometrical parameters given there, and be mindful of this relation as well. So from here on, like your next logical step is to plug in and like write down the full equations, expand it. Same you will do for CM trim. You will expand it and then you will put it equals 0. And you will find that there will be only two variables which are not known to you, alpha trim and I tail. The rest of the coefficients, all coefficients such as CL naught, CM naught, etc., you can derive all of them using the geometrical, either they are given in the question or you can derive them using some approximation or some rule of thumb approximation that you seem fit. That's one of the trickiest part of this course is that what do you think is a good approximation for a missing data point if you think you can't do it, but it's doable? So that is one of the points of this office hour session also, to let you know that it's doable. Um, yeah, and you can get the rest of the parameters as well. Now, okay. Also, there is a lot of information as well, like in the question, like it's a rectangular wing. So your average chord is going to be the same as, like, the chord at each section is going to be the same as the average chord length, and so on and so forth. So read the question like very carefully. Okay. So you will basically get both alpha trim and I trim, and it will work out for you. Not I trim, I tail, alpha trim. And then it's the same thing again with the most forward CG location. If I tail max is going to be plus minus 25 degrees. So you already know that it's not like positive, negative deflection. How does it move the CG forward and backward, the most forward CG location? So first think whether the most forward CG location should be at plus 25 or minus 25, and why it should be. You don't need to do math to um, come down to the conclusion that, okay, should I be plugging in plus 25 or minus 25? It's a concept there. If you feel doubtful about that, shoot me an email that I'm not able to understand plus or minus 25. And then you go ahead, plug it into the equation, the last equation that you write, where you write down the complete expression for. So for the second part, you first have to like think, do I use plus minus 25 for iTail, and why? You have to justify, and that physical explanation has been discussed in class. Go watch the video if you haven't. And finally, um, I think alpha max is also given. Yes, alpha max is also given. Excellent. So you put in alpha max, you assume that your CGs are the most forward, and then you go ahead, get the CM alpha most forward. And once you have CM alpha most forward, you already have CL alpha. So from the CM equation, you get CM alpha most forward. Actually, this is not a good acronym. CM alpha most forward. And then we know that, static margin relates neutral point and CG. So maybe you already have the information about static margin. Think about it. If you already have this information about static margin, we know that this is CM alpha by CL alpha minus. Now, CL alpha does not change with CG location. This is a fixed quantity, which we could have determined from the previous analysis, part one's analysis. And then CM alpha will be most forward. So once you have that, I think it will be very straightforward to get the most forward location for CG. Any questions from two, please?
No, not right now.
Okay. Let's move on to problem. Do I have time? I have plenty. Okay, so question 3 says an airplane has the following pitching moment characteristics at the center of gravity. XCG is given to us. Okay. So XCG is given to me. CM naught DCM by DCL and CM delta is given to me. So remember that DCM by DCM by DCL is CM alpha by CL alpha. I have discussed this in my last discussion session video. If you haven't watched it from last Friday, that would be a good point to review it. That why C DCM by DCL is same as CM alpha by CL alpha. If the landing gear deployment causes an increase in drag coefficient at the landing flight condition by 0.05, estimate the induced pitching moment due to landing gear deployment. assuming that the line of action of the additional drag force is 50% C bar below the fuselage reference line. If the airplane is loaded so that the center of gravity position moves to XCG. Okay, let's do first part. So I would very strongly suggest that make a diagram for this one to understand it better. So it's saying that, let's say this is the fuselage reference line and we deploy the landing gear, and because of that there is an additional drag, and this drag is acting 50% of the chord below the fuselage line. So some, oh shoot, okay. Hmm. So 50% of, so somewhere so 50% like somewhere down below, here you have the extra drag delta T due to the landing gear. Now see, the position of the landing gear does not matter along the x-axis point. Why? Because the moment that would be coming would directly be a pitching moment, a negative pitching moment, and this distance is the only distance that you require, which is given to be 50% of C bar. So you can get the change in drag, and once you know the change in drag, you can get the change in moment due to this drag. Once you know the change in moment due to this drag, you can obviously calculate, like the first part is done, like what is the induced pitching moment, and obviously it's going to be negative because remember that, do I have the model here? I don't have it right now, but yeah, remember that when you have an aircraft, then if the nose is pointing this way, then this is negative pitching moment and this is positive pitching moment. It's opposite to the right hand thumb rule that you usually use in physics. If the airplane is loaded so that the center of gravity position moves to 0.15, can the airplane be trimmed during landing where CL is 1.0 and assume that delta E max is plus minus 20 degrees? So again, during landing, we put it to maximum elevator deflection at negative values. Why? Because remember that positive deflection is down for an elevator and negative deflection is up for an elevator. And why do you physically need that? Again, go and review lecture 6 for that. Um, and it's telling me that the CG location has moved to 0.15 and now I need to trim it. So I could have, um, since I already know DCM by DCL, I know the static margin. And since I know the static margin and the CG, I know the neutral point. And once I know the neutral point, I think I can find the most forward CG location. And if the airplane can be trimmed with that. Does that answer questions? Or do you have something specific to discuss from question 3?
No, or no. I need
Okay,
to try it. Yeah.
okay. And then the last question. A 2375 horsepower piston engine turning a 32-inch 5-blade propeller shows so on and so forth. When the airplane is flying at 200 miles per hour, the propeller is turning at so much RPM. The change in normal force component with the propeller angle of attack for this propeller and operating condition is 0.27 per radians. The propeller is mounted 9 feet 4 inches forward of the center of gravity, which is located at 0.25 cbar. Estimate the static margin with or without the propeller effect. Is the propeller contribution destabilizing or stabilizing? The airplane has the following geometric and aerodynamic characteristics. So this is a little bit of an involved question. So I'm not going to, like, it's not difficult, it's just long, a little bit longer and involved. So first of all, as always, I suggest you to draw figures because this is going to clarify a lot of stuff for you. So the first geometrical piece of information is that, let's say your leading edge of the wing is here, right? And like positive x-axis starts here and your CG is somewhere here. So xCG is 0.25 C bar. And the propellers are mounted 9 feet 4 inches forward. So the propellers are mounted somewhere here. And this location is 9 feet 4 inches. Convert it into SI units if you're more comfortable with that. Okay, and what it is saying that when the airplane is flying at 200 miles per hour, the propeller is turning at 300 rotations per minute. The change in normal lift force coefficient with propeller angle of attack for this propeller and operating condition is 20.27 uh, 7 per rad. So what is it saying that, okay, you don't need to worry about, so obviously this propeller on its own will have some drag and some lift at the propeller, drag at the propeller, okay. It's already been told to you that in this course we don't worry much about drag, so you can assume that we are not going to be focused on drag at the moment. But it is saying that the lift changes at 0.27. So obviously it is telling us that CL alpha for the propeller is 0.27 per rad. So remember that data is always not provided in this, like in this format here. Okay, sometimes data could be provided in this, in words. The change in lift coefficient with propeller angle of attack for this propeller is 0.27. Okay, so now we are going to be writing the contributions coming from the propeller, and we are ultimately going to cast it in something times alpha plus a constant. Um, and to do that, you'll need these terms like CL alpha, which are coefficients of the alpha term. Estimate the static margin with and with. So you obviously can estimate the static margin without the propeller. First of all, that would be an easier job to do. And then you go ahead and estimate. Basically, you add the pitching moment contribution from the propeller to the pitching um, equation, pitching moment equation. So first you write down the pitching moment equation as usual for the aircraft without the propeller, and go ahead and estimate the static margin, which is straightforward. That gives you confidence that you understand the concept. And then copy down the same pitching moment equation, add the contribution from the propeller. So how will you add the contribution? There is you can assume that there is like no inherent pitching moment coming, that you can make an assumption that um, for the propeller, like the pitching moment is only coming from the lift. So the then it will have a positive pitching up moment. Like if you see, this is the CG, this is the propeller, and you take the moment up. And that contribution has to be added to the moment equation. And from that, you are going to rederive the static margin. And then you are going to tell us that whether it has a destabilizing or stabilizing effect. If the static margin increases, then it's stabilizing because the neutral point is moving further away from the CG, right? And if the static margin decreases, it means the neutral point is coming closer to the CG, which is destabilizing. So I think, yeah, that's all for homework two. Anything specific?
Can I just clarify something from number one?
Yep.
Um, so I did catch that the CL alpha tail that they give us is the 2D one,
Mm-hmm.
but to get the 3D, do we need to use the 2D or is that not related?
No, for 3D you need to do 3D. Yes, you're doing it for a business aircraft. So CL alpha tail is for 2D, and you need to get the 3D CL alpha to plug it into the equation.
Right. So is like to get the 3D one, do I need to use the 2D one? I'm a bit confused of how to get the 3D one.
Yeah. So if you go and look in the notes that Professor Taha has provided, the first chapter is about all these short formulae. So go from 2D to 3D. This is the expression to be exact. So CL alpha, capital alpha means 3D. CL alpha in 3D is equals to, wait, hold on. Oh yeah, CL alpha is equals to pi AR tail aspect ratio of the tail divided by 1 plus root over 1 plus kappa square of the tail, where kappa tail is given as pi AR tail divided by C small l alpha tail. So you plug in
Okay.
C small l alpha tail here, you have the aspect ratio of the tail multiplied with pi, get kappa, plug kappa here, AR tail, and then you get CL alpha. And
Okay.
this, like,
That makes sense.
all of these small tricks will be there in the, like, for these, you can refer to the first chapter in the notes that Professor Taha has. So Professor Taha has posted a PDF of all the mathematical relations, like equations and formulae that will be required in this course, which you can use as a ready reference from time to time. And these ones, like converting from 2D to 3D, downwash, relations of sweep, you'll come across sweep next week or this week probably. And how to relate sweep to geometrical parameters. All of these are there in the first chapter of those notes. Yep.
Okay. Awesome. Thank you.
Okay. Yeah, sure. And here are a few questions that Jenna sent me. So, when drawing the planform area of wings, why do we project the wing shape going into the fuselage? Um, it's just a convention. That's how it's defined in the standard manuals, and it doesn't have that much of an effect. Like we can add to make it even more practical, like when you do practical aerospace design, it's very detailed, and to account for all these assumptions and approximations, we'll introduce correction coefficients later on. So if you do happen to become an engineer like aerospace design or something, you will come across, we do it very accurately, don't worry. Yeah. Are the elevator and flap areas also planform areas? Yes. I mean, for the tail, like, yeah, they are counted in planform areas. For like wings, they will be counted as planform area. A flap will be part of planform area, and for tail, the elevator will be a part of the planform area. Like without deflection, when the elevator is not deflected, and when the flaps are not deployed at that time, they are taken into account for the total area. Yes. What is the physical significance of chord gamma in the diagram? I couldn't get. Oh, it's not chord gamma. It's chord sub R. It's not chord sub gamma. It's chord sub R. So chord sub R means chord at the root, and chord sub T means chord at the tip. Root is the end of the wing near to the passengers, and tip is the wing part of the wing, like away from the fuselage or the passengers. Why is the graph of tau applicable for any control surface or lifting surface area? It's an empirical approximation. It's an empirical approximation. Those properties might vary, but because we use symmetrical tails, and I mean, if you go into detailed design, there are a lot of things, like you could probably become a tail design engineer. But yeah, for now in this class, we'll use that for simplicity. I think that's all the questions, and I'll end the session today.